Hello everyone and welcome to the video version of this lecture. Because you're watching this lecture as a video, you will be unable to use the interactive features such as clicking the continue button. So when I say give this question some thought and click the continue button when you are ready, please pause the video at that point and give the question some thought. Remember, if you're not putting pen to paper during the lecture and working through the problems on your own, you are not learning. Enjoy. Greetings one and all and welcome, wamkelekile, to this Physics Ulu 1B on making meaning with units using a device called the ratio table. My name is Dr. Philip Southey and I'll be your narrator for this particular Ulu. So we're looking at units and how these reveal relationships between physical quantities. So this is where we're heading. By the end of this section, you should hopefully be able to easily solve this example. I'll read it with you. A large rectangular beam of light of side 2 meters is incident on a flat surface. Over a period of 21 seconds, the radiant exposure or fluence on the surface is measured to be 4,200 joules per square meter. Calculate the power of the light source in watts, i.e. joules per second, to two significant figures. So, even though you've never heard of radiant exposure or joules per square meter, hopefully by the end of this section you'll be able to make sense of those units and solve this problem. But let's start nice and slow with the familiar concept of speed. Explain to your grandmother what it means for a leopard to have a top speed of 16 meters per second. Give that some thought, and when you're ready, click the continue button. So hopefully you said something like, Gogo, this means that the leopard can cover a distance of 16 meters in 1 second. Or, Omar, for every 1 second that goes by, that leopard moves a distance of 16 meters. Now I want to show you how you can represent this in what I call a ratio table. So speed is actually a ratio between distance and time. In this case, distance is measured in meters and time is measured in seconds. So we can insert that information by saying 16 meters is traveled in 1 second. So that first line of the ratio table can be read in a few ways. 16 meters in 1 second, or 16 meters for every 1 second. But importantly, we can also use this word per. 16 meters per 1 second, which is often just simplified to 16 meters per second. Let's remind you of the formula from high school. Speed is distance divided by time. We've got 16 meters divided by 1 second, which gives us 16 meters per second. Make that relationship between the formula and the ratio table. Now, if I ask you, how far does the leopard travel in 2 seconds? I want to show you how we can easily use the ratio table to answer that. Hopefully this insults your intelligence, but we just want to get a feel for the ratio table. So 16 meters in 1 second, we want to know the distance it travels in 2 seconds. On the right-hand side of that ratio table, we have to multiply by 2. What we do to the right-hand side, we do to the left-hand side. 16 multiplied by 2 gives you 32 meters traveled in 2 seconds. So that second line of the ratio table can be read as such, 32 meters traveled in 2 seconds. But importantly, that word per is reserved for when we have that number 1. 16 meters per 1 second. Here's another example to do with speed, but here you have to keep your wits about you. Let's read it together. Your brother is doing his grade 7 homework. He's told that a toy train travels 10 meters in 5 seconds, but he divides 5 by 10 on his calculator and gets 0.5. Can you explain to him what the number 0.5 means in this context? Before you do, let's just see what he should have done, right? He was trying to calculate the speed, so he should have taken the distance of 10 meters and divided it by the time of 5 seconds to get 2 meters per second. Let's remind ourselves of what that looks like in a ratio table. So speed is a ratio of distance to time. The information that we're given is that the toy train covers 10 meters in 5 seconds. If we want to get the speed, we want to calculate the number of meters per second. In other words, the number of meters per 1 second. How do we go from the 5 on the right-hand column to the 1? We're going to divide by 5. What we do to the right-hand side, we do to the left-hand side, and we see that in the ratio table, that second line can be read as 2 meters per second. That's the speed. So what your brother actually did was he took the 5 and he divided it by the 10. Let's have a look at what that looks like in the ratio table. So the toy train travels 10 meters in 5 seconds. Your brother takes the 5 to the right-hand column and he divides by 10 to get that 0.5. Can you do the same division for the left-hand column? See what you get? And then see if you can use that second line of the ratio table to explain to your brother what he's calculated. After you've given that some thought, press the continue button. So what you do to the right-hand side, you do to the left, and you get 1 under the meters column. And you can read that line as saying, younger brother, you've just calculated that the train travels 1 meter in 0.5 seconds. But because we have this 1 over here, we can also use the word per. Can you see how you would use the word per in this case? 0.5 seconds per 1 meter. Yeah. What does that mean? Buddy, it means it takes 0.5 seconds for every 1 meter traveled. 0.5 seconds per meter. That's what you've calculated. Have a look back at the equation on the left-hand side. 5 seconds divided by 10 meters. Hopefully you're okay with me writing that as 0.5 seconds divided by 1 meter. And we can therefore write that as 0.5 seconds per meter. Now this physical quantity, which makes perfectly good sense, doesn't have a name. So let's give it a name. I'm going to call it the deeps. I don't know if you've seen what I've done there. Speed backwards. So we can say, Buddy, you have calculated the deeps of the toy train. 0.5 seconds per meter. For every meter that this train travels, it takes 0.5 seconds. Next, period and frequency. You remember from high school, the period is defined as the number of seconds it takes to complete 1 cycle. The frequency, the number of cycles completed in 1 second. Oh, 1 cycle, 1 second. I'm feeling a purr coming on here. So we have a playground merry-go-round that completes 7 cycles, i.e. 7 rotations in 17.5 seconds. I'm going to model this merry-go-round as a circle. I'm going to paint a circle, little yellow dots on the right-hand side, and there is 1 rotation or 1 cycle. We're going to ask you some questions about this, but first, a technical interlude. You can use hints to answer questions in this Ulu. So I'm going to ask you to take your mouse cursor and move it over that text box that says hint. And your mouse cursor should become a little hand icon, which means that you can click on that text box. And do that now. And a second text box should pop up. Now, sometimes what can happen is that if you take your mouse cursor over that second text box, you'll also see a hand icon, which means that you can click on it. And if you do that, voila, you should see a third text box that pops up. When you've run out of things that you can click on, then you're going to go to the bottom right-hand corner and click on the continue button. So there are 3 questions, 3 hints. When you're ready, click the continue button. First question, put this information in a ratio table. There it is, 7 cycles in 17.5 seconds. Remember, the important step was to identify the 2 physical quantities that we wanted to relate. In this case, it was the number of cycles and the time in seconds. Second question, calculate the period of the merry-go-round, the time it takes to complete 1 cycle. So we want a 1 in the left-hand cycles column. How did we get from 7 to 1? We divided by 7. What do we do to the left? We do to the right. And we get 2.5 seconds. So to complete one cycle, a merry-go-round takes 2.5 seconds. Can you say that second line of the ratio table using the word per? 2.5 seconds per cycle. There it is in formula form. If you prefer that, 17.5 seconds divided by 7 cycles gives you 2.5 seconds per cycle. And could you explain to your grandmother what that means? Gran, it means in order to complete one rotation or one cycle, it takes 2.5 seconds. Last question, we're going to calculate the frequency of the merry-go-round, the number of cycles completed in 1 second. So we want a 1 in that right-hand time column. In order to get to the 1, I'm going to divide by 17.5, which I also do on the left-hand side. Hopefully you can see that you could just as easily get the answer if you divided by 2.5 to go from the second line to the third line of that column. In either case, you're going to get the answer of 0.4 cycles in 1 second. Using the word per, 0.4 cycles per second. There it is in formula form. We took 7 cycles divided by 17.5 seconds, and we got 0.4 cycles per second. There's another unit that we can use for cycles per second. Do you remember what it is? Hertz, 0.4 hertz. Can you explain to your grandmother what that means in the case of the merry-go-round? Well, let's think about what half a cycle is. Yeah? So that is about 0.5 cycles. So to get 0.4 cycles, let's back it up a bit. There we go. And we know that it takes 1 second to complete 0.4 cycles. There we go, Gran. So can you guys tell me where will the merry-go-round be after 1 more second? How far would it have rotated? It will rotate to 0.8 cycles. Yeah, it completes 8/10ths of a cycle in 2 seconds. So here's a physical quantity you might come across in your academic careers: volumetric flow rate in cubic meters per second. A pipe delivers 60 cubic meters of water every 60 seconds. Put this information in a ratio table and calculate the volumetric flow rate of this pipe, even though you don't have a formula. When you've done that, click the continue button. Right, welcome back. So what are the two physical quantities that are in relationship here? Yeah, cubic meters gives us a measure of volume, and seconds, as you know, gives us a measure of time. You can see the wording's changed slightly here, 60 cubic meters of water every minute. I just want to show you that if I don't specify the units of the column, I can just as easily as say that's the same thing as writing 60 cubic meters in 60 seconds. It's still volume as a ratio to time. Now I want to get the volumetric flow rate in cubic meters per 1 second. That's what per second means. Divide by 60 on the right, divide by 60 on the left, and I find that the volumetric flow rate is 1 cubic meter per second. Can you explain to your grandmother what that quantity means? Can you make physical sense of that quantity? Draw a diagram of a pipe to aid your explanation, and press the continue button when you're ready. Right, welcome back. So there's my pipe. Let's fill it with water. And now I just want to consider 1 cubic meter of that pipe. 1 cubic meter of water. Now what happens to that cubic meter in 1 second? In 1 second, 1 cubic meter of water flows out of the pipe. The volumetric flow rate is 1 cubic meter volume every second. Right, here's a physical quantity I just made up. Rainfall flux in liters per square meter. A small town measures an annual rainfall flux of 515 liters per square meter. Can you put that information in a ratio table, please? Click continue when you're done. So remember, your first step is to identify which physical quantities are in relationship here. Liters per square meter means that we have a ratio between volume, which in this case is measured in liters, and area, which is measured in square meters. So there's our information, and that first line of the ratio table means that we have 515 liters per square meter for every square meter. Can you explain the meaning of 515 liters per square meter to your grandmother? Include a rough sketch, and when you're done, click the continue button. Welcome back. So first let's start with a square meter. So Gogo, there's my square meter, and every square meter of this little town received 515 liters of rain. Gogo, this means that every 1 square meter of ground, that's an area of 1 meter long by 1 meter wide, receives 515 liters of rainfall in 1 year. That's 515 1-liter Coke bottles, that you could empty onto that 1 square meter of ground. Now, I just want to emphasize that word every. For every square meter of this little town receives those 515 1-liter Coke bottles worth of water from the sky. If the area of the town is approximately 9 million square meters, can you calculate the approximate annual rainfall in liters? Press the continue button when you've done that. So we had 515 liters per 1 square meter, but now we're dealing with 9 million square meters. So we multiply by 9 million on the right, multiply by 9 million on the left, and we get 4.63 times 10 to the 9 liters. So if you want to say that second row of the ratio table in an English sentence, you could say, this small town receives 4.63 billion liters of rainfall every year. Now here's something interesting to tell your grandmother. The relationship between rainfall in millimeters, which is what we hear on the weather report, and rainfall flux, which is the units that I just made up in liters per square meter. So if you Google, what is the meaning of 1 millimeter of rain? This is what you find. 1 millimeter of rain refers to the depth of rain that would be received in 1 square meter. Let's draw a diagram. So here's a box that has a length of 1 meter, a breadth of 1 meter, and importantly, a depth of 1 millimeter. Now I'm going to fill that box with rainwater, and I want to know what is the volume of water that we have in that box. So I'm going to go length times breadth times height. Well, obviously I've changed the height into meters, and hopefully you should see that that volume is 0.001 cubic meters. We're going to chat more about unit conversions in the next Ulu, but for now, if you just want to Google what's the relationship between cubic meters and liters, you'll find that 0.001 cubic meters is the same volume as 1 liter. So that box contains 1 liter of water. In other words, 1 millimeter of rain translates to 1 liter of water in a single square meter box. So, a rainfall of 1 millimeter is the same thing as a rainfall flux of 1 liter per square meter. So if you look at the weather map on the right-hand side, that little red dot is Colesberg in the Eastern Cape. And on that wonderful Saturday in August 2021, Colesberg received 100 millimeters of rain, which means that every square meter of dry Karoo felt that day received 100 liters of rain. Did you know that Stellenbosch's annual rainfall is about 515 millimeters per year, which means that every square meter of Stellenbosch receives 515 liters per year. Now, Stellenbosch has an area of about 9 square kilometers, or 9 million square meters, which means that in the previous question, you guys calculated that every year Stellenbosch receives about 4.63 billion liters of rain. Right, folks, I think we're ready to tackle that problem we came across at the beginning of the section. A large rectangular beam of light of side 2 meters is incident on a flat surface. Over a period of 21 seconds, the radiant exposure or fluence on the surface is measured to be 4,200 joules per square meter. Calculate the power of the light source in watts. We're not going to do this in one gulp. We're going to do it step by step. Here's the first step. When you've given it a go, click continue. Welcome back. So fluence is a ratio of energy to area, and in this case we have 4,200 joules per 1 square meter. Importantly, in this particular problem, this ratio table holds for a time period of 21 seconds. So explaining it to your grandmother, you're going to say, Nkono, this means every square meter area of the surface receives 4,200 joules of energy over a period of 21 seconds. Right, let's zoom in on that surface area. And here, part 2, give it a go, and then click the continue button. Right, so we know that this rectangular beam of light is of side 2 meters, which means that the area of the beam is 4 square meters. Now from our ratio table, where we entered the information of the fluence, we know that 4,200 joules of light energy is transmitted to each 1 square meter over a period of 21 seconds. So in 21 seconds, every square meter absorbs 4,200 joules of light energy, and we have 4 square meters. So if we look back at our ratio table, we have 4 square meters. We need to multiply the right-hand side by 4 to find the total energy absorbed by the surface, which is 16,800 joules over a period of 21 seconds. And the final step of this question, to calculate the power, there are some hints you can use. When you're ready to check your answer, click the continue button. Right, so we're setting up a ratio table of energy to time, remembering that in this particular context, this ratio table applies for that area of the rectangular beam, which is 4 square meters. So for those 4 square meters, we know that 16,800 joules are delivered or transmitted over a time period of 21 seconds. Look over to the left-hand side. We're told that over a period of 21 seconds, 16,800 joules of light energy is transmitted to 4 square meters of area. Now, on the right-hand side, we're re-representing that in another way. Over an area of 4 square meters, 16,800 joules of light energy is transmitted over a time period of 21 seconds. To find the power, we want joules per second, joules per 1 second. Dividing by 21 on the right-hand side, dividing by 21 on the left-hand side to get 800 joules per second. That is your power. And just for completion, we can use a formula in this case as well. Power is energy over time. That's 16,800 joules over 21 seconds, 800 joules per second, 800 watts for that area of 4 square meters. Here's a similar problem for you to try on your own. There are a variety of ways of solving this, but if you get stuck, you can check out the steps that I've suggested on the left-hand side. Remember, if you're using hints, if you're clicking on that hint and you get a text box, you might also be able to click on that text box to get some more information. If you want to check your answer, you want to click the answer text box in the bottom right-hand corner, and once you've done that, you can click the continue button. That's it, folks. Thanks for watching this learning unit. We'll have some more problems for you in level 2.